So today we're going to look at proof in the coordinate plane. By the way, these notes are separate from what's in your journal, so you will need a separate sheet of paper. So if you don't have some paper and some pencil, you'll probably want to get that and pause the podcast while you're doing that and come back to it. You will also need to know these formulas. So if you don't have those written down, you may want to jot these down somewhere on a piece of paper, unless you have them memorized. But these are formulas we've dealt with all year. You should be pretty comfortable with them. All right, proving things in the coordinate plane. I want to prove that triangle PSR is an isosceles triangle. Now, how can we go about doing that? Well, basically, we can prove things about side lengths, and we can prove some things about angles, but I can't really measure angles in the coordinate plane using distance, midpoint, and slope formula. We need some more advanced math for that, which we are not ready for yet. So what we can prove are parallel lines and perpendicular lines, so we can show right angles. Here I want to prove that something's an isosceles triangle. So how do I prove that something's isosceles? We got to know what isosceles means. Isosceles is going to mean that we have at least two congruent sides. So I need to prove that at least two sides are congruent in this triangle. Now, how am I going to show that things are congruent using distance, midpoint, or slope formula? Well, the easiest way to show congruence, right back here, distance formula. Distance formula shows that segments are congruent by finding the lengths of the segments. So essentially what I want to do is I want to be able to find the length of this segment and the length of this segment and show that they're congruent. And by doing that, I've proven that this is an isosceles triangle. We don't need to find the length of the third side because, again, isosceles means at least two sides congruent. Once I have two, I can stop. So what do? We plug into our distance formula. And again, make sure you're designating which segment you're finding so anyone who's reading it can follow along with what your work is saying. So if I'm going to find PS first, I'm going to say PS equals. I'm going to plug in my coordinates for that. My x coordinates are -3 and 0. My y coordinates are 0 and 4. And now we just do our simplification. That's -3 squared plus, positive. No, that's -3 squared. I was right the first time. Plus -4 squared. Remember, whenever we square a negative, it still winds up positive. So square root of 25, which is exactly 5. There's PS. And now we're going to do SR. I'll switch colors for the rest of this. And again, the x coordinates are 0 and 3 and 4. And again, we just work our way through the distance formula. And I know it seems like I'm doing a lot of steps, but it's because I want to show all my work. I'm going to make fewer mistakes the more work I show. And so therefore, I have now proven, because I've shown they have the same length, I have proven that PS is congruent to SR because they have the same length. So not too tough. We're just using things we've seen before. Obviously, key to this whole process is remembering what the definitions of words are and which formula measures which thing. So let's go back and look at that one more time. Distance formula we use to measure congruence. Slope formula, parallel or perpendicular. And midpoint, midpoint can also show a midpoint. Midpoint can also show us some congruence. If I can show that something is a midpoint, then we can use definition of midpoint to say that the two parts that make up the larger segment, the two half segments are congruent if something's a midpoint. So it can be used for that, but only in special circumstances. Let's try another one. Here I want to prove the triangles are congruent given that GJ bisects angle OGH. So again, like any good proof, we're going to kind of draw our picture first and indicate what's given to us. So GJ bisects angle OGH. So there's angle OGH. with GJ as a bisector. So already we know that these two angles are going to be congruent. So if I have two angles congruent already, now I have a couple choices as to how to prove these triangles congruent. Again, I've got all my shortcuts: side, 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 angle, side, angle, side, angle, 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 side, and HL. Now in this case, since I already have the one pair of angles, that probably is going to eliminate side, side, side as a choice. It's pretty clear these are not right triangles, so HL is out. So now I have to look, what's going to be my best choice? Side, angle, angle, or angle, angle, side. And again, in the coordinate plane, it's very difficult to prove that angles are congruent unless they're right angles. And with no right angles here, it's going to be almost impossible to do angle, side, angle, or angle, angle, side. So side, angle, side is probably going to be my best choice. In fact, it's going to be my only choice. So how do I do that? Again, we make a little plan. So if I can show that GO is congruent to GH, and GJ obviously is congruent to itself, I don't need to prove that because that's just a reflexive. So really I can do this with one distance formula measurement, because I already have the congruent angles, I already have a reflexive. All I need to do is show that GO is congruent to GH. And again, we do that with distance formula. And we'll need our coordinates. G is at 3, 5, and O is at 0, 0. And it's pretty mechanical from this point. Square root of 34. And now we do the same thing for GH. I'm going to leave that to you in the notes. And once we have that, obviously we have our congruent triangles by side, angle, side. In fact, the biggest thing is to make a plan. And once you have the plan, the execution is pretty simple here, as long as you know your formulas. So what are different ways I could prove triangle ABD congruent to triangle CBD? Again, if you're not sure, plans, just list out your shortcuts and see which ones are possible. So plan one, well, the easiest way in the coordinate plane always to show that triangles are congruent is just to go ahead and use side, 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 because it can just do distance formulas on all three sides. So plan one would be side, side, side. Find the length of AB and AC, and then AD and DC. Show those are congruent. We have the reflexive, BD is reflexive. So 4 distance formulas, and we're pretty much done. Plan 2, I'm going to take a slightly different tactic, and we're going to use the midpoint formula just a little bit here. So because if I could show, basically I'm going to use side, side, side again. And again, we're going to show AB congruent to AC. Okay, that's distance. And BD is reflexive. So nothing to calculate there. But I could show that D is the midpoint of AC. And if I show D as the midpoint of AC using midpoint formula, that implies by definition of midpoint that AD is congruent to AC. So we get that side, side, side again, but by a slightly different technique. Instead of having to find the actual distance for AD and DC, we could use the midpoint formula and then use the definition of midpoint to make our conclusion, instead of having to do that. Our third method here might be to, since I do have what appears to be a right angle here, I could probably use HL and use slope formula to show that BD is perpendicular to AC. And then again, AB congruent to BC by distance formula. Sorry, the tail of the D didn't show up there. Okay. And then BD congruent to itself reflexive. And I've got an HL proof here. So there's a lot of different ways when you're given a picture sometimes to prove that the triangles are congruent in the coordinate plane. We aren't always limited to just one choice. So part of it is figuring out what possibly applies and then figuring out a way to get there using distance, midpoint, and slope formulas. All right, this is an interesting one. Place in the coordinate plane and find the indicated length. This is a right triangle with one length of 8 and another of 6. Now, if I'm going to place a right triangle, I'm going to be smart. I'm going to put one spot here at the origin. I'm going to make my sides horizontal and vertical. Okay, there's my 6. There's my 8. I'm halfway done with this problem already. Because those two sides I don't need to use distance formula for, they're horizontal and vertical. They're really easy to work with. So if you're going to place a right triangle, do it that way. If you're going to place a rectangle, I would, again, put one of the vertices right at the origin, at 0, 0. Keep as many zeros in my coordinates as possible. It makes distance and slope and all the other formulas very simple to work with. You've got to find three things. First, the length of the hypotenuse. So again, a length. That's going to be a distance formula. So that's going to be 6 minus 0 squared plus 0 minus 8 squared. So 6 squared plus negative 8 squared. 30 plus 6 plus 64 is the square root of 100, which is 10. Fantastic. We've got A done. B, find the midpoint of the hypotenuse. Okay, midpoint formula. Midpoint formula, we just take the x coordinates, divide by 2, and we take the y coordinates and divide by 2. So 0 plus 6 over 2 is 3, and 8 plus 0 over 2 is 4. So the midpoint is at 3, 4. I could even plot that. In fact, it'd probably be a really good idea to plot that. Okay, there's my midpoint. Finally, part C says find the distance from the right angle vertex to the midpoint of the hypotenuse. So it wants this. So again, we know that the coordinates of this are 3, 4. So we go do another distance formula. And that's pretty straightforward. Give myself a little more space here. Now I want you to notice something. The distance from the vertex of the right angle to the midpoint of the hypotenuse is 5. Length of the hypotenuse was 10. So if this is the midpoint of the hypotenuse right here, and the whole length is 10, each of those is 5. And all three of those distances are exactly the same. Isn't that interesting? We'll talk about that a little bit more as time goes on. But kind of interesting little conclusion there. All right. All the work we're going to be doing here in the coordinate plane is going to be pretty concrete. We're going to have definite coordinates. And again, you're going to need to know your formulas. So make sure that you know which formula to use, and you know what the formulas are. Absolutely critical. If you don't know that, you can't do these problems. So we'll see you in class.